Good day and welcome to the introduction to programming in C++ of the Diverse Node Mobility Front-End Development Program. Today we will be discussing Chapter 2 that talks about advanced flow control and data aggregates. So here, going to share my screen to you guys. So for the conditional statement, here we have the if and else statement, the more powerful conditional instruction. So the conditional statement more conditional than before. We conclude our last discussion on conditional statements with the promise that we were going to introduce a more complex and flexible form soon. We started off with a simple phrase which read, if the weather is good, we will go for a walk. Note, it doesn't say anything about what will happen if it rains cats and dogs. We only know that we won't go outside, but what we could do instead is not known. We may want to plan something in case of the bad weather too. In this case, we can say, for example, if the weather is good, we will go for a walk, otherwise, we will go to a theater. This sentence makes our plans more resistant to the whims of fate. We know that we will do if the conditions are met, and we know that we will do if not everything goes our way. In other words, we have a plan B. The C++ language allows us to express these alternative plans. We do it with a second, slightly more complex form of the conditional statement. Here it is. So here's the algorithm for if else statement, conditional statement. If true or false condition, perform if condition is true, and else perform if the condition is false. So now we have a new word, else, here. This is a keyword or reserved keyword. The statement beginning with else tells us what to do if the condition specified for if is not met. So the if execution goes as follows. So if the condition is true, the perform if condition true is executed and the conditional statement comes to an end. And if the condition is false, the perform if condition false is executed and the conditional statement comes to an end. By using this form, the conditional statement, we can describe our plan just like this. So we have um, example earlier that if the weather is good, we will go for a walk, and else we will go to a theater. And whether the weather is good or bad, then we will have our lunch. So just like the other simpler instructions we have already encountered, both if and else may contain only one statement. If you want to add more than one instruction, then you have to use a block as in the example on the right. So if the weather is good, we will go for a walk and have fun. Else, we will go to a theater and enjoy the movie. Or whether the weather is good or bad, we will have our lunch. Right. So now it's time to discuss two special cases of the conditional statement. First, think about when the instruction placed after if is another if. So this is what we have got for this Sunday. If the weather is fine, we will go search for a nice restaurant. If we find a nice restaurant, we will have lunch there. Otherwise, we will eat a sandwich. If the weather is bad, we will go to the theater. If there are no tickets, we will go shopping to the nearest mall. Complicated, right? Let us write the same thing in the C++ language. Now, let us look at the code. So here, the first is if the weather is fine or good, we will go to search a restaurant and we will have lunch there. Otherwise, we will eat sandwich. All right, so if the weather is bad, so here, otherwise, we will go to a theater. And if there's no available ticket here, we will go for a shopping to the nearest mall. Right. So two important points to note. First, using the if statement like this is known as nesting. Remember that every else refers to the closest former if that doesn't match any other else. This is how the ifs and else's pair up. Look at how the indentation improves readability and emphasize the nesting of the inner conditional statement. Pretty, isn't it? All right. So remember the K and R style. So we will have our first pair of if else. So here's the indentation. After that, another pair of if else inside the if. So we have indented it here, and also it's paired else, just like the another if else pair after the else. All right. So that is how if else nesting works. So this second special case is somewhat similar to nesting, but with an important difference. Again, we are going to change our plans and express them as follows. If the weather is fine, we will go for a walk. Otherwise, we get tickets. We will go to the theater. Otherwise, if there are free tables at the restaurant, we will go for lunch. If everything fails, we will return home and play chess. Can you see how many alternatives we have listed here? Let us write the same scenario in C++. So first, as you can see, there are not only one pair of if else, but this is called cascade, and that is we are going to use else if. Okay, so there are a lot of alternative. For example, if the weather is good, we will go for a walk. Else if ticket is available, go to a theater. And else if uh, table if table is available, then we will have go for our lunch. And if not, if the weather is bad, tickets is unavailable and tables is unavailable, then we will play chess at home. So when you assemble subsequent if statements, it is called a cascade. Notice again how the indentation improves the readability of code. Now put conditional statements to the back of your mind. Let us subconscious do the work and think back to our old friend types in char and floats. It's time to meet their siblings. So as you can see, we have if, then else if your option is more than two, then we will use else if, and then for the last option, we will just use else. All right, so let's go to 2.2, and this is the more talks about more types and when we use them. All right, so let's have 2.2 more types and when we use them. Wouldn't it be great if the developer's life could be organized well enough with only type int to operate with integers, type char to manipulate characters, and type float to work with floating point calculations? Unfortunately, such a narrow repertoire of types raises some problems. Most of the computer in current use store ints using 32 bits or 4 bytes. This means that we can operate the ints from the range of negative 214748364 to 214748367. It may happen that first, we don't need such large values. If we are counting shapes, we are unlikely to have 2 billion of them. So why waste the majority of these 32 bits if we don't even need them? Second, we need much larger values. For example, if we intend to calculate the exact number of humans living on Earth, in this case, we need more than 32 bits to represent that number. Third, we only need two different values to represent the on and off states of or the true or false condition, which don't actually have a numerical interpretation, although we can use make presumption of for them and use one as on and zero as off, for example. And fourth, the number of inhabitants on Earth will never be a negative number. It seems a real waste that up to half of permissible range will never be used. For these reasons, the C++ language provides some methods to define exactly how we intend to store large or small numbers. This allows the compiler to allocate memory either smaller than or larger than usual. We can also declare that we guarantee that the value stored in the variable will be non-negative. In this case, the width of the variable's range doesn't change, but is shifted towards the positive numbers. This means that instead of the range negative 214748364 to 214748367, we have the range of 0 to 429496725. So to specify our memory requirements, we can use some additional keywords called modifiers. So we have long, used to declare that we need a wider range of ints than the standard one. And short, used to declare that we need a narrower range if ints than the standard one. And lastly, unsigned. So used to declare that a variable will be used only for non-negative numbers. This might surprise you, but we can use this modifier together with the type char. We will explain it soon. Okay, so let us look at the sum example. Okay, so here's the next slide, for example. All right, so the counter variable will use fewer bits than the standard int. In this case, the range of the variable will be suppressed to the range of negative 32768 to 32767. So the word int may be omitted as all the declarations lacking a type name are considered to specify int by default like this. So instead of writing short int counter, you can just simply omit the int and just declare short then the variable which is counter. So the ants variable will use more bits than the standard int. So for example, 64 bits, so it can be used to store numbers from the range of negative 9223372036885. So this is so much a large number. Can you reach such huge numbers? So note, you can again omit the word int. So instead of writing long int ants, you can say long ants and omit the reserved keyword int. So if we decided that a variable will never be a negative value, we can use the unsigned modifier. As before, we can omit the int. So instead of saying unsigned int positive, so we understood that the variable will be always positive. So we can add unsigned here and omit the int. Okay, so we can also mix some of the modifiers together. Take a look. So we can remove the word int and the declaration will preserve its meaning. Unsigned, long, int, huge number. Instead of adding int again, so we can omit that and just say unsigned, long, huge number. Okay. So a more modest example goes like this. So we can also say unsigned short int lamps. So instead of declaring that, we can omit the int and then say unsigned short. So remember guys that if you are adding the two modifiers, make sure that the unsigned will always be on front. Okay, so the long and the short modifiers must not use in conjunction with the type char y and must not be simultaneously in a single declaration, but there is nothing preventing us from using the unsigned modifier with a variable of type char. What do we get from such declaration? Don't forget that we are not allowed to omit the word char. Most of the compiler is current use assume that the char's are stored using 8 bits or 1 byte. That may be enough to store a small value such as the number of months or even the day of the months. If we treated the char variable as a signed integer number, its range would be -128 to +127. So if we don't need any signed value, as in the example here, its range shifts to 0 to 255. This may be enough for many applications and may also result in significant savings in memory usage. Now, pay attention to this. So far, we have used integer literals, assuming that all of them are of type int. Its general rule, but there are some cases when the compiler recognizes literals of a type long. This will happen if, first, a literal value goes beyond the acceptable range of the type int. The second, a letter L or uppercase L or lowercase l is appended to the literal, such as 0 uppercase L or 1981 L. Both of these are literal. Both of these literals are type long. So, by the way, guys, that if you are going to use modifier in character type, you don't omit the char data type, just like this. And don't forget that we are not allowed to omit the word char. So don't forget that. But if we are using int data type, then we can omit that. The short and long modifiers cannot be used with a float, but there is a type named double. Variables of type double may differ from the variables of type float, not only in range but also in accuracy. So what does this mean? Well, the data stored in the floating point variable has finite precision. In other words, only a certain number of digits are precisely stored in the variable. For example, we expect that the value 1 1 1 1 1 and so on and dot 1 1 1 and so on will be stored by a specific type of computer as this value. We can say that the variable saves only 8 precise digits. This is within the expected accuracy of 32-bit long floats. Using a double guarantees that the variable will save more significant digits, about 15 to 17. This is where the name double comes from. Its accuracy is doubled comparing to float. So we talked a little while about how computer addition is not always commutative. Can you guess why? This is why this is. So imagine that you have to add together a large number of floating point values. Some of them are very large and some of them are very small, just like here in this example. If a very small float value is added to the large one, you could end up with a surprise. Let us return to the previous example. Assume that our computer only saves 8 precise digits on any float. If we add these two floats, we will probably get this answer 1111111065600000 as the result. The lesser value simply vanishes without a trace. We can avoid these effects when we add or subtract the numbers of type float. This phenomenon is one of the so-called numerical anomalies. All right, so in memory of George Boole, who's George Boole? So George Boole from 1815 to 1867 was an English mathematician, philosopher, and logician, and we are talking about him for a very important reason. One of his most important achievements was algebraic logic, referred to by Boole himself as the laws of thought. Algebraic logic does not operate on numbers but only on two truth values and doesn't use standard arithmetic operation like addition and multiplication, but conjunction, disjunction, and negation. taking into the account the fact that virtually all modern computers are built using Boole's theorems, we can say without exaggeration that Boole was actually one of the founders of IT. There is a type in the C++ language whose name commemorates George Boole. The type Boole is a very intriguing type. Variables of this type are able to store only two distinct values, and that is true and false. Note, all of these words, bool, true, and false, are keywords. Don't forget that. Take a look at the example on the right. Okay, so bool, developer is hungry, is equals to false. Take a look at the alright, so we have this declared a variable there. Neither its name nor its value requires additional comments. There are many contexts where this variable may be used. One of the most spectacular is the following. If developer is hungry, then its block would says have lunch, and developer is hungry is equals or not. This is a negation, and developer is not hungry. So the exclamation mark we have used in the assignment is a negation operator. It is an unary prefix operator that changes the logical value of its arguments. Because of the operator, true comes false and vice versa. As you see, having lunch changes the logical statement of one of the most important factors of the programmer's well-being. To be honest, the bool type is only a very special variant of the int type. It is very short. Variables of this type occupy only 8 bits, which is still too much because 1 bit would be enough. It behaves like an int. Inside the expression, true is equivalent to 1, while false is equivalent to 0. We will return to this type and values soon to George and to George Boole's algebra and logical operators too. Okay, so we have bool and true and false. So now we are going to show you some simple but complete programs. We won't explain them in detail because we think that the comments inside the code are sufficient guides. All of these programs solve the same problem. They find the largest several numbers and print it out. So let us start with the simplest case, how to identify the larger of the two numbers. So this code in the editor are program for identifying the larger of the two numbers. So first, we have the header file. Okay, so here we have hash include iostream and then forget. So since we are using C++ programming language, we are going to use using namespace std before the main function will be written. So since this is the title of our program, finding the larger of two numbers, and here, so let's start for the main function. So first, we have declared two variables named number 1 and number 2. And we have also another variable which is named max. So here, we will save the larger number here. And for the two numbers, for number 1 and number 2 variable, and we have cin. Okay, so number 1, and you know guys that cin is the scanf of C++ language, and here we temporarily assume that the former number is the larger one, and we will check it soon. So we have an expression max is equals to number 1. So here's the checking or the conditional statement. We check the if the assumption was false. So here we if number 2 is greater than max, then max is equals to number 2. Then C out, we will print as a result. The larger number is max, which is equivalent to number 2. So we just assume that the maximum or the larger number is number 2 or number 1. So when finish our program, then we will add return 0 on the last part of our editor. So here another example for the program. This is entitled finding the largest of three numbers. So we have a header file, one header file, and that is iostream. So we have four variables, and that is number one, number two, number three, and the max or the larger number will be saved in this variable. So we have going to read the three numbers, which is C in. We are going to use a greater than. C in, then number one, number two, then number three for the reading of the three numbers of the value. So if you are going to create or make the user input the value of number one, two, and three, you are going to declare here C out. All right. So we temporarily assume that the former larger is the is larger. The former number is the larger one, and we will check it soon. So the maximum number is number one. Then if number two is greater than max is equals to number two, and number three is greater than max, then the maximum number is then the max is equals to number three. Then we are going to see out. We will use less than, then the larger number is then max, and then and L stands for new line, right? So by this point, you should be able to write a program that finds the largest of 4, 5, and 6, or even 10 numbers. You already know the scheme, so the extension of the program doesn't need to be particular complex. But what happens if we ask you to write a program that finds the largest of the hundreds of number? Can you imagine that codes? You will need hundreds of declarations of variables of type in. And if you think you can do that, then try to imagine writing a program that finds the largest of the million numbers. Imagine that the code contains 99 conditional statements and 100 scene statements. So let us ignore the C++ language for the moment and let's try to analyze the problem while not thinking about the programming. In other words, let us try to write the algorithm, and when we are happy with it, then we will try to implement it. So we are going to use a kind of notation that is not a programming language at all. It could be neither compiled nor executed, but informalized is a formalized, concise, and readable, and we called it pseudocode. There is an example of pseudocode in the right, and take a look at what's going on. So we have declared here as you can see, this is a pseudocode, cannot be filed nor executed, just an algorithm that the human can read the logic of it. So we have a max variable that is equals to negative 999999999 and read. And the first thing that we will do is read the number, which number will be entered by the user, and we will have our if statement or conditional statement. If number is equals to negative 1, then print the maximum, then next stop. Then if number is greater than max, then max is equals to number. Then go to number 2. So first we can simplify our program if at the very beginning of the code we assign the variable max with a value which will be smaller than any of the numbers entered. We will use negative 999999999 for this purpose. Second, we assume that the algorithm doesn't know in advance how many numbers will be delivered to the program. We expect that the user will enter as many numbers as she or he wants. The algorithm will work equally well with the 100 or 1000 numbers. How do we do that? Well, we make a deal with the user. When the value is negative 1 is entered, it will be a sign that there is no more than data of the program should end its work. Otherwise, if the entered value is not equal to negative 1, the program will read another number and so on. The trick is based on the assumption that any part of the code can be performed more than once, in fact, as many times as you need it. Performing a certain part of the code more than once is called a loop. You probably already know what a loop is. See steps 2 and through 5. Make a loop. Here, making a loop. So, yeah. So, we are going to repeat it again. The process, right? So, that is a looping. Can we use a similar structure in the program written in the C++ language? Yes, we can. And we are going to tell you about it soon. So how much time do you usually need to wash your hands? 10 seconds, a minute, or more? Or does this depend on how dirty your hands are? When your hands are very dirty, you wash them for a very long time. Otherwise, it takes less time. Would you agree with this statement? While my hands are dirty, I am washing my hands. Note that this record also declares that if your hands are clean, you won't wash them at all. So now, you've learned one of the loops available in the C++ language. In general, the loop looks like this. While, and then we have conditional underscore expression, then the statement. So if you think it looks similar to the if instruction, you are quite right. Indeed, there's only one syntactic difference. We replace the word if with the word while. The semantic difference is more important when the condition is met. If performs its statement only once, while repeats the execution as long as the condition evaluates to true. So let us look at some specific comments. First, if you want while to execute more than one statement, you must use a block. Take a look at here. So here we use block since we are going to use more statement here. So let us use block, and block is curly braces, open and close. So one or more instructions executed inside the loop are called the loop's body. So if the condition is false the first time around, the body is not executed even once. All right. So the remember the analogy of not having to wash your hands if they are dirty. Okay, so the body should be able to change the condition value, and because if the condition is true at the beginning, the body might run continuously to infinity. Notice the act of washing changes the state of impurity. So here is an example of a loop that is not able to finish its execution. This loop will infinitely print I am stuck inside a loop on the screen. Okay, so here we have a while, then the conditional statement is one, the parameter is one. So this means that is true or no. No other conditional statement is limited here. We have C out, I'm stuck in the loop, and then end. So this is a new line. It will um, create or it will print infinite sentence, which is I am stuck inside a loop. So let us go back to the algorithm we talked about recently. We are going to show you how to use the newly learned loop. By the way, we want to introduce you to one more novelty. So far, we have declared variables in one place and assigned values to them in another. We can combine these two steps by declaring the variables and assigning the value at the same time. This is done by adding the equal sign or the assignment operator followed by an expression whose value is assigned to the variable at the time of its creation. For example, if you need a variable that needs the value of 0, then you can do this. So int and then variable and then 0. So that would be the assignment operator is equal. So now we have a new word in our vocabulary. The part of the declaration on the right of the equal sign is called the initiator. The initiator you saw before was a literal, but you can use more complex expression like these ones. Okay, so we will be using initiators often. They are very convenient and useful. So the initiator would be 3.1415. And then this is the literal, and we can not only have the value itself, but we can have expression that are also considered as initiator. Okay, so let's analyze this program carefully. Let us locate the loose body and figure out how the body is exited. So check out the code and try to implement the algorithm we talked about earlier. So first, we are going to find out um, how the body executed, and after that, we will have how the body is exited. So first, we have the header file, which is hash include iostream. Then using namespace std, then we have main function, and here this variable is a temporary storage for incoming numbers, and cin, then the number, get the first value, and the next one would be we have declared um max as the variable, and we have assignment operator that is equals to number. And if the number is not equals to 1, then we will continue. So continuing that is a loop for a while. And is the number greater than max? Then if yes, then the update the maximum number, then max is equals to number. Then get next number is seen, then number. So print the largest number, then see out the largest number is, then finish the program execute successfully. So if you like to download this code, you can download this file and then run that into your um, Apache NetBeans IDE. Or if you're having a hard time using that, you can use IDE1, an online IDE, in running the C++ code. So this program counts odd and even numbers coming from the keyword. Have a look at it. So here, certain snippets can be simplified without changing the program's behavior, but take a look at the next slide. Okay, so let's take a look in this code. As you can see, we have the main function, and we have the variable events and odds, and we have an initiator that is equals to 0, and we will have a declared a number variable, and we will store the incoming numbers here in this variable. And first, we have cin to read the number, and next, we are going to terminate the execution, which is while if number is not equal to 0, then if number is modulus 2, then this is odd, right? Because because adds always have a remainder 1, right? Odd number. And else it is equals to evens. And then we have increment. So then increase even counter, and then read the next number, which is C in the number. All we need to do is print this result, and that is for C out. If even numbers, then evens, and then odd numbers, then odds, which is their variable. So try to recall how the C++ language interprets the truth of a condition, and note that these two forms are equivalent. While number is not equal to 0, then the loop, and the while number then it have its block. Okay, so take note that this conditional statement sample are equivalent. So the condition that checks if a number is odd can be coded like this. So if number modulus 2 is equals 1, then, or if number modulus 2 is, and then its statement. So that is um the modulus expression, getting the odds for, and that is the expression on how getting the odd numbers. And we will have get use of modulus 2. So we guess that nothing surprises you, right? But there are two things that we can write more compactly. First, the condition of the while loop. Okay, so first, here's the main function. In counter is equals to 5, and then while counter is not equals to 0, then we will have C out, I am an awesome program, then counter minus minus. So since counter is equals to 5, then it will get the awesome and the statement or the sentence, I am an awesome program. The program or the console will print this until we will get the increment of counter, which is until 4 and 5. So it will probably give us, it will give us another value for counter, which is 4, since we use decrement here. So another change requires us to have some knowledge of how the post decrement works. So we will use it to compact our program once again. So we have in counter is equals to 5, then while counter, then C out. So we will have the same result. So here we have um, counter is equals to 5, then we have the decrement inside this one. Counter equals minus minus, then C out, I am an awesome program. So we already know that the while loop has two important features. First is it checks the condition before entering the body, and the second, the body will not be entered if the condition is false. So these two properties can often use unnecessary complications. For this reason, there is another loop in the C++ language which acts the mirror image of the while loop. We say this because in that loop, the condition is checked at the end of the body execution, and next the loop's body is executed at least once even if the condition is not met. So this loop is called do loop. It's simplified, the syntax is listed here. So here's the syntax: do, then the statement, then the while condition. So remember that this checks the end of the body execution, and the body execution is the loop's body is executed at once even if the condition is not met. So if you want to execute a body containing more than one statement, you need to use a block. Remember? Okay, so curly braces for the block. So let us return to the program that searches for the largest number. Firstly, we will use the do loop instead of while for teaching purposes. Secondly, we remove the vulnerability involved the excessive trust in the user's goodwill. Our new program won't be misled by entering the value of -1 as the first number. Here is the program. So here we have a declared number, three variables, and that is number, max, and counter. So we have an initiator here, negative 100,000, and then counter for 0. And we have the do loop here. Okay, so remember that it will execute our program whether, since we don't have, it will execute the program whether it is the condition is not met uh, or or vice versa. So we have C in with the number, and then if number is -1, then counter plus plus. And if number is greater than max, then max is equals to number. Then while number is not equals to -1, then if counter and see out the largest number is, and else see out are kidding, you haven't entered a number. Okay, so take a look. We use the counter variable to count the numbers entered so we can instruct the user that we cannot search for the greatest number if the no number is given. As we have read at least one number, it makes sense to use the do loop. We use this approach in the program. So the last available kind of loop in C++ language comes from the fact that sometimes it is more important to count the turns of the loop than to check the conditions. So imagine that the loop's body needs to be executed exactly 100 times. If you want to use the while loop for that purpose, it may look like this. So we have int I, and then I is equals to 0, then while and I is less than 100, then the body goes here. So I plus plus. So we can distinguish three independent elements. So they are the initiation of the counter, which is I is equals to 0, and checking of the condition, which is I is less than 100, and the modification of the counter, which is the I increment. So it is possible to create something like a generalized scheme for these kinds of loop. For it is initialization, then while, and then goes the checking, and then the body goes here, and then modification or modifying. So this way of coding the loop is very common, so there is a special brief way in writing in C++ language. And here we have gathered all the three decisive parts together. The loop is clear and very and easy to understand. Its name is for. So we have the for loop, and we have for, then initialization, then semicolon, checking, and then modifying. So we will have our example. So here, for the for loop can take the following form: for, then parenthesis, I is equals to 0, semicolon, I is less than 100, and then I increment. So the variable used for counting the loop's turns is often called a control variable. Notice that the control variable doesn't have to be declared before it is used within the for loop. It can be declared inside the loop with the initialization. This is the red one, so you don't need to declare that before the loop. So, but in this case, it will be available during and only during the loop execution. So here's the example: for, and then int is equals to 0, then I is greater than 100, less than 100, and I increment. Right, so the for loop has an interesting singularity if we omit any of its three components. It is presumed that there is a one there instead. One of the consequences of this is that the loop written in this way is an infinite loop. Well, the conditional expression is not there, so it is automatically assumed to be true. And because the condition never becomes false, the loop becomes infinite. So since we don't have any conditional here, so it becomes infinite. So all we need to do is set a limitation, right? So let us look at the short program whose task is to write sum of the first powers of 2. So let us look. So the exp variable is used as a control variable for the loop and indicates the current value of the exponent. The exponentiation itself is replaced by multiplying by 2. And since 2 to the power of 0 is equals to 1, then 2 times 1 is equals to 2 to the power of 1, and 2 times to the power of 1 is equals to 2 to the power of 2, and so on. So to answer this question, what is the greatest exponent for which program is still prints the result? So we have our program here, and we have the initialization for pow, and that is equivalent to 1. Then if int is exponent is equals to 0 and exponent is less than 16, then exponent plus plus. Now see out 2 to the power of, then exponent, then is power, then we have the new line, then power So this is the modification. Power equals power times 2, then return 0. So here guys, that I have run the sample program here. So let us run that using our Sandbox Interactive IDE, online IDE. So here we have hash include. I just copy and paste it here inside the editor. So using namespace std, remember that we are using C++, and we have the main function. And here guys, that how do we get that output? So can you see the limitation here, which is less than 16? So what is less than 16? That is 15, right? So that would be set to 15, which is limiting the infinite loop. So here we have plus plus, and according to exp, that is equals to 0. So we start from 0, then plus plus. So this is increment 0 to 15, and then so we get this using the power. And power, how do we get that? Because of the modification, which is power times equals to 2, which is that is how we get that answer. So as you can see in the C out, we have 2 to the power of exponent, which is starting from 0. Here is the power, which is equivalent to 1, starting from 1. And power, here we start from 1, and the modification of that would be here. And then we get this this answers of the powers until 15. Right, so next, let's have the next slide. So far, we have treated the body of the loop as an indivisible and inseparable sequence of the instructions that are performed completely at every turn of the loop. However, as a developer, you could faced with the following choices. First, it appears that it is unnecessary to continue the loop as a whole, and we should stop executing the loop's body and go further. Second, it appears that we need to start the condition testing without completing the execution of the current turn. So the C++ language provides us to with two special instructions to implement both this task. Let us say, for the sake of the accuracy, that their existence in the language is not necessary. An experienced programmer can code any algorithm without these instructions. The famous Dutch computer scientist named Edsger Dijkstra proved it on in 1965. These additions, which don't improve the language's expressive power but only simplify the developer's work, are sometimes called syntactic candies. These two instructions are break. So break. So this is a reserved keyword. This keyword exits the loop immediately and unconditionally ends the loop's operation. The program begins to execute the nearest instruction after the loop's body. And then we have continue. This is also a reserved keyword that behaves as the program suddenly reached at the end of the body. And the end of the loop's body is reached and the condition expression is tested immediately. So both these words are keywords. Now let us look at the two examples. We will return our program that recognizes the largest numbers entered. We will convert it twice using both instructions, analyze the code, and judge whether and how you would use any of them. So the break variant goes here. Okay, so we have the break. Okay, so we use break here, break keyword, and note that the only way to execute the program is to perform the break, as the loop itself is infinite for loop. Okay, so we have this, and we have number, max, and counter. And then since this is an infinite, then we will read the number. Then if number is equals to -1, we will going to break the execution, since it will run an infinite loop. So counter plus plus, and then if another if here, if number is greater than max, then max is equals to number. Then if counter, see out that the largest number is max, which is equivalent to negative, and it will also define, or it will be processed using this conditional statement. Then else, see out or kidding, you haven't entered a number, so it will read if the user haven't entered any value. And now let's have the continue variant. Here we have continue keyword was used in our program. We have also another, so we have also number, max, and counter. So do while loop, we have used do while loop. This is reading the number, which is cin, and then we have if number is equals to -1, then we will continue, then counter plus plus. So this variant is continue, or this keyword let the execution continue from the word itself. So we have number is greater than max, then number is equals to number, then while then number is not equals to -1, then if counter, then we have see out the largest number is max, then else. Okay, so have you noticed that the condition conditions we have used so far are very simple, quite primitive in fact. The conditions we use in the real life are more complex. Let us look at the following sentence. So if we have some free time and the weather is good, we will go for a walk. We have used the conjunction and, which means that going for a walk depends on the simultaneous fulfillment of the two conditions. So in the language of logic, connecting conditions like this is called conjunction. And now another example. If you are not in the mall or I am in the mall, one of us will buy a gift for mom. The appearance of the word or means that the purchase depends on at least one of these conditions. So in logic, a compound like this is called a disjunction. So clearly that the C++ language needs to have operators to build conjunction and disjunction. So without them, the expressive power of the language would be substantially weakened. They are called logical operators. So we have condition and disjunction. So what do you think is their operators? So here, a logical conjunction operator is in C++ language is a digraph, which is ampersand ampersand. So that is the logical operator for conjunction. It's a binary operator with a priority that is lower than the one expressed by the comparison operators. It allows us to code complex conditions without the use of the parentheses like this one. So we have counter greater than 0 and value is equals to 100. So this is the conjunction of the two condition. So the result of the and operator can be determined by the so-called truth table. If we consider the condition of left and right, the set of the possible values of the arguments and corresponding values of the conjunction looks like this. So we have left and right, and left and right. So we already this is the result of the conjunction. So false and I mean false and false. The answer is false. False and true. Then the answer is false. True and false, the answer is false again. And true and true, the answer is true. So all we need to do is look if there is a false keyword or here, so the answer will be always false. So the exception to this is true. The conjunction of true to true will be equals to true. Okay, so the dysfunction operator is a digraph bar. It's a binary operator with its priority lower than and just like the plus compared to times. Its truth table look like this. So this is the disjunction. So false, false or false. We have false, false or true, we have true. So this dig graph bar is read as or, right? Okay, so false, true or false then equals to true, and true or false is equals to true. So as you can see, guys, that if there is a true keyword here, then the answer will be true. So in this case, so the left and right value will have the same false value, so the answer would be false. But if you see that there is only at least one true, then the answer is true. So that is for disjunction or for or. Okay. So in addition, there is another operator that can be used to construct conditions. It is a unary operator. It is a unary operator performing a logical negation. So its operation is simple. It turns truth into falsehood and falsehood into truth. This operator is written as a single character exclamation mark, and its priority is very high. The same as the increment and decrement operators, its truth table is very simple here. So we have a negation here. So false, then it will become to true, and true will become false. So just vice versa, or the negation or the opposite value of them. All right, so the following condition are equivalent of each other. So we have variable is greater than 0, and then not variable is less than greater than or equals to 0. So this is equivalent, guys. And while variable is not equals to 0, is equals to not variable is equals to 0. Right, so you may remember the De Morgan's laws from school. They say that the negation of the conjunction is the disjunction of the negations, and the negation of the disjunction is the conjunction of the negation. So here is how we use that. So not P and Q is equals to not P or not Q. Do you agree with that? So this is commutative, right? So here, not P or Q is equals to not P and not Q. So let us try using, so this is how we write that in C++ language, not how we use the parentheses to code and expressions. So by the way, none of the above two arguments operators can be used in the abbreviated form of the known op. This exception is worth remembering. So logical operators that take their arguments as a whole regardless of how many bits they contain. The operators are aware only of the values 0 or false, which means false or not 0, or true, which means true. The result of their operations is either the value 0 for false and 1 for true. This means that the snippet on the right will assign the value true to the j variable if I is not false. So otherwise, it will be false. So we have bool, then I, then j. So j is equals to not l. This is I. Okay, so as you can see, the otherwise it will be false. All right, so why it become false? Because if we are converting I and not I, then it will become j. But we have another not here, the negation, so it will become another it will become again an I, right? So that's why this expression is false. So there are, however, four operators that allows you to manipulate single bits of data. They are called bitwise operators. They cover all the operations we mentioned before in the logical context, and one additional operator. This is so-called XOR, or stands for as exclusive or, and denoted as caret, and here all of them. So we have ampersand bitwise conjunction, we have bar bitwise disjunction, we have tilde the bitwise negation, and we have caret for bitwise exclusive or for XOR. Let us make it easier. So AND requires exactly two ones to provide a one as a result, and or the bar requires at least one to provide one as a result, and we have caret for XOR is exactly one to provide one as a result. So let us mention something important here. Arguments of these operators must be integers. So we cannot use floats here. So the difference in the operation of the logical and bit operator is important. The logical operators do not penetrate into the bit level of its argument. They are only interested in the final integer value. Bitwise operators are stricter. They deal with every bit separately. If we assume that the int variable occupies 32 bits, you can imagine that a bitwise operation has a 32-fold evaluation of the logical operator for each pair of bits of the arguments. This analogy is obviously imperfect as a real world. All these 32 operations are performed at the same time. So let us look at the bitwise truth table here. So we have a bar, which is disjunction. We have conjunction for and caret for the XOR. So 0, let us use OR here. 0 or is equals to 0. 0 or 1 is equals to 1. 1 or 0 is equals to 1. 1 or 1 is equals to 1. Let's have AND. 0 and 0 is equals to 0. 0 and 1 is equals to 0. 1 and 0 is equals to 0. 1 and 1 is equals to 1. Let's have XOR. 0 XOR 1 equals to 0. 0 XOR 1 is equals to 1. 1 XOR 0 is equals to 1. And 1 XOR 1 is equals to 0. All you have, as you can see, you have noticed that the XOR is only, you can get a value, the result of 0, if the given is both the same, is the same. Just like both 0 and both 1, you can get 1. But if it is different value, then you will get 1. Different value will get 1. So negation is very simple, just the opposite value. Just like 0 is equals to 1 and 1 negation is equals to 0. So we will now show you an example of the difference in the operation between logical and bit operations. Let us assume that the following declaration has been performed. Int I is equals to 15 and j is equals to 22. If we assume that the ints are stored with 32 bits, the bitwise image of the two variable will be like this. So guys, this is just a binary, right? So it is stored in 32 bits. So this declaration is given. Int log is equals to 1 and j. We are dealing with a logical conjunction. Let us trace the course of the calculations. Both variables I and j are not zeros, so they will be deemed to represent true. So if we check the truth table of the AND operator, we can check that the result will be true, which the integer is equals to 1. This means that the bitwise image of log variable is this. So the bitwise operator of log is in this image. So now that the bitwise operator here it is. So in bit is equals to I and j, the AND operator will operate with each pair of corresponding bits separately, producing the values of the relevant bits of the result. Therefore, the result is this. So bit is equals to 110. So this is a binary in the 32 bits was in the 32 bits memory stored. So these bits correspond to the integer value of 6. So let us try the negation operators now. First, the logical one, we have int log neg. So we have not I. The log neg variable will be set to 0. So its image will consist of zeros only. So the bitwise negation goes here. Int bit neg is equals to negation of I. It may surprise you to learn that bit neg variable value is equals to negative 16. If it surprises you, try to spend some time looking into the secrets of the binary numeral system and the rules governing so-called two complements numbers. So it makes for good bedtime reading. So remember the bit value is equals to negative 16. So we can use we can use each of the previous two arguments operators in their abbreviated forms. These are the example of the equivalent notation. So we have the simplified form. Here's the simplified form. So you don't need to repeat the variable itself. So here, instead of using x is equals to x and y, we can say put the and here, the operator here beside the x, and then remove this, and then we have equals, then copy the y. So here's the simplified form, just like or we remove x and the bar just here, replace it here, and then the equals, and then the y. We have the XOR or the caret here, x is equals to x caret and y, or in the simplified form, x XOR is equals to y. So we will now show what you can use bitwise operators for. Imagine that you have to write an important piece of an operating system. You have been told that you're to use the variable declared in the following way. You have int, then flag register. The variable stores information about various aspects of the system operation. Each bit of the variable stores one yes or no value. You have also been told that only one of these bits is yours. Bit number 3. Remember that the bits are numbered from 0, and bit number 0 is the lowest one, while the highest is 31. So the remaining bits are not allowed to change because they are intended to store any data. Here's your bit mark with the letter X. So here, okay, so you may face the following task. Number one, check the state of the bit. You want to find out the value of the bit. Comparing the whole variable to 0 will not do anything because the remaining bits can have completely unpredictable values, but we can use the following conjunction property. So x and 1 is equals to x, and x and 0 is equals to 0. So if we apply the AND operation to the flag register variable along with the following bit image, okay, so we can get this. Okay, so 1, we have here 1. So 1 stands for true and 0 for false. So we get that. So we are here. Can you check this code? So if flag register and the mask, and we will perform the my bit is set, or else my bit is reset. So number 2, reset your bit. You assign a 0 to the bit while all the other bits remain unchanged. We will use the same property of the conjunction as before, but we will use a slightly different mask just like this. So note that the mask was created as a result of the negation of all bits of the mask variable. Resetting the bits is simple and look like this. Choose, okay, so here it is. So flag is equals to register. Flag register is equals to flag register and negation of the mask. And we have here, to simplify this form, we have flag register and equals to negation of the mask. So number 3, set your bit. You assign a 1 to your bit. Well, all of the other bits remain unchanged. We will use the following disjunction property. So x or 1 is equals to 1, x or 0 is equals to x. We are now ready to set your bit with one of the following instruction. Flag register is equals to flag register or the mask, or how to get that, to simplify that, flag register or equals the mask. So number four, to negate your bit, you replace one with zero and zero with one. Let's use an interesting property of the XOR operator. So we have x XOR one is equals to not x, and x XOR one is equals to x. And negate your bit with the following instruction. So following register is equals to following flag register is equals to flag register XOR the mask, or to simplify that, flag register XOR equals the mask. So how to do the single plus plus language offers, sorry. So the C++ language offers us yet another operations relating to single bits is called shifting. It applies only to integer values, and you cannot use it with floats as arguments. You use this operation unconsciously all the time. How do you multiply any number by 10? Take a look. So 1, 2, 3, 4, 5 times 10 is equal to 1, 2, 3, 4, 5, 0. As you can see, multiplying by 10 in just case of shifting all of the digits to the left and adding a 0 to the right. How do you divide by 10? Let us look. So 12340 divided by 10 is equal to 1234. All you need to do is shift the digit to the right. So the computer performed the same kind of operation with the ones difference as 2 in the base of the binary numbers, not 10. Shifting a value 1 bit to the left corresponds to multiplying it by 2, respectively, because shifting a 1 bit to the right is like dividing by 2. Notice that the right most bit is lost. So the bit shifting can be first logical if all bits of the variable are shifted. This kind of shifting takes place when you apply it to the unsigned integers. So what is unsigned integers? There are all positive, no negative, non-negative integers. So next is arithmetic of the shift amidst the so-called sign bit. In the two complement notation, the role of the sign bit is played by the highest bit of the variable. If it's equals to 1, the value is treated as a negative. This means that the arithmetic shift cannot change the sign of the shifted value. The shift operator in C++ language are pair of digraphs, um, less than, and greater, clearly indicating which operator at which direction the shift will act. The left argument of this operator is an integer value whose bits are shifted. The right argument determines the size of the shift. It shows that this operation is certainly not commutative. The priority of this operator is very high. You will see that in the updated table priorities at the end of this section. So we have value. So this is shifted to the left. Okay, so we have value, then shifted to the right in bits. Assume that the existence of the following declaration: int sign is equals to -8, then we have var s. Unsigned, then we have unsigned variable is equals to 6, then var u. And take a look at this shift. So equivalent to this division by 2, shifted to var s equals to -4, then var s equals to sign shifted to 1, then we have equals to multiplication by 4, var s is equals to -2, var s is equals to sign shifted to 2, shifted to sign, then var equivalent to division by 4, shifted to variable u, or var u is equals to 1, then var u equals to unsigned shift to 2, equivalent to multiplication by 2, var u is equals to 10, then var u equals unsigned, then 1 shifted to unsigned. Right, so and here's the updated priority table containing all of the operators we have introduced during the current lesson. So here is the updated priority table. We have the unary and binary. And the unary is for negation. We have not here, type, increment, decrement, plus and minus, and also negative. This is multiplication, division, and modulus. We have binary. We have plus, equals, plus and minus, Okay, so this is positive and negative. Right, so that is the updated table. As you can see, the um, bitwise operator have a lower priority in this table. Right, guys, let's have 2.5. The switch, the switch condition statement, the difference phase of if. So case and switch versus if. So as we already know, an if cascade is a name for a construction of code where many if constructions are placed consecutively one after another. As in the following example, we have if if I is equals to 1, then see out only 1. Then else if I is equals to 2, I want more. Then else if I is equals to 3, see out not bad, and else see out okay. So of course there are no obstacle to using and maintaining a code like this, but there are few disadvantages that may be discouraging. The longer the cascade, the harder it is to read and understand and it is intended for. Amending the cascade is also hard. It is hard to add a new branch into it, and it is hard to remove any previously created branch. The C++ language offers us a way to make this selection easier. By the way, this is only more syntax candy. You can manage without it, but don't hesitate to use it when your ifs started to growing extensively. So we have switch. All right, so let us look at the snippet on the right. So we have switch, then case 1, see out only 1. Case 2, see out only one more. Case 3, see out not bad. And case 4, see out okay. So it is an example of how to replace an if cascade with a specialized instruction. So note that the word switch and case are keywords. So here is keywords switch, case, and also break. So the new instruction is named switch, and it is in fact a switch. How does this work? How does it work? First, the value of the expression enclosed inside a parenthesis after the switch keyword is evaluated. So this is sometimes called as a switching expression. Then the block is searched in order to find a literal preceded by the keyword that is equal to the value of the expression. When a case is found, then the instructions behind the colon are executed. If there is a break among them, then the execution of the switch statement is terminated. Otherwise, all vacant instructions are executed until the end of the block is reached or another break is met. What happens if the switching expression has a value that does not occur in the cases? The answer is simple: nothing. None of the branches of the switch statement are executed. So here, let us modify the requirements. We can assume now that our program will be satisfied. It will say, okay, if the I variable is equals to 4 or 3, does this mean that we have to create two branches for both possibilities? Thankfully not. All we have to do is add more than one case in front of any branch, like this. So we have case 1, case 2. So as you can see, uh, if I is equivalent to 3, then it will uh, it will not, or it will the console will not give us any paragraph any statement just like this. Okay, so that is how we use switch. So we can also assume that our program has no opinion on where the I values are other than specified so far. And we want the program to express this clearly. Have we made a million new cases covering the entire int types range? No, we can use a generalist case that covers all the events that are not mentioned in the previous cases. This is how it looks. So note the default keyword is a keyword 2 here after the last case. So don't forget to use break after the cases here. So leaving out the keyword is one of the most common mistakes that developers make, not only in the beginning of their career. Simple, right? And how elegant. Let us think about the following important remarks. First, the value after the case must not be an expression. As you can see, this okay, so case this is not an expression, right? Containing variables or any other entities whose values are not known at the compilation time. The case branches are scanned in the same order in which they are specified in the program. This means that the most common selection should be first. So now, say goodbye to switch statement. It's time to tackle the important issue of arrays. Alright guys, so we will continue arrays in our next session, the chapter 2 part 2. And for now, that concludes the chapter 2 part 1 of the diverse node mobility front end development program. So thank you very much guys and have a good day.